right, question number 13. If the sugar in question number 12, that one, were transcribed to a linear sugar, all of the hydroxide groups on carbons 2, 3, and 4 would be option A, on the right-hand side and left sides of the molecule. So basically, are they on opposite sides of the molecule? B, they're on the right-hand side of the molecule. C, they're on the left-hand side of the molecule. And D, it's impossible to tell if they would be on the right or the left-hand side. Now, we're talking about a beta sugar here, carbons 2, 3, and 4. They are all pointing downward. And we can look at this and say, if they are pointing down, they are going to be on the right side of my molecule. So the best answer for this, for number 13, is B. If they were pointing up and down, then you would have some combination of right and left, or if they were all pointing up, then they would be all on the left-hand side, but they are uniform. Now, the sugar shown below is a disaccharide of A, 2 glucose molecules, B, 1 glucose and 1 C4 epimer of glucose, C, 1 glucose and 1 C3 epimer, or D, 2 sugars in which neither are glucose. Okay, so if we look at this sugar on the right-hand side, this one right here, we've got carbon 2, 3, and 4 with a pattern of down, up, down. So that is glucose. If we look at the sugar on the left, we've got down on carbon 2, up on carbon 3, up on carbon 4. So that's the C4 epimer of glucose. So our best answer here is B, 1 glucose and 1 C4 epimer of glucose. That's number 14 is B. 15, a glycogen molecule generally has A, many reducing ends and 1 non-reducing end, B, many non-reducing ends and 1 reducing end, C, an equal number of reducing and non-reducing, or D, no reducing and no non-reducing. Okay, so a glycogen molecule, this is effectively asking, like, this is what a glycogen molecule looks like. This is a reducing end. All of these ends are non-reducing ends. So our best answer for this, many non-reducing and 1 reducing end. So B is our best answer for this question. That's number 15 is B. Number 16, which amino acid is best described as a polar amino acid? Okay, alanine, leucine, isoleucine, glutamic acid. E, glutamic acid. Question 17, which amino acid will have a negatively charged R group at some pH? So we're speaking specifically about the R group. Arginine will either be positive or nothing. Lysine will be positive or nothing. Asparagine will be nothing. It's a neutral polar amino acid. Glutamic acid is going to be negatively charged at some pH, so the correct answer for number 17 is C. All right, number 18. Which pair correctly matches the single letter code with the full name of the amino acid? So if we look at these, I think a good way to start is just to ask, is the first letter the same? And let's go with D. M is methionine. That is correct. R is arginine. Glutamine is Q. Asparagine is N. E is glutamic acid. L is leucine. D is aspartic acid. R is arginine. P is proline. So D, M, methionine is our best answer. Number 19, which pair correctly matches the 3-letter code three-letter amino acid code with the full name? Okay, well, we've got ASN is asparagine, ASP is aspartic acid, GLU is glutamic acid, GLN is glutamine, ILE is isoleucine, LEU is leucine, Me is nothing, and methionine is MET. Okay, next up is number 20. What is the significance of the pi? So every molecule's got a pi. Every ionizable molecule is going to have a pi. And a molecule that, so The point at which a molecule has no charges. That's incorrect. It has no overall charge. Does it have charges? Yes, it does. It has positives and it has negatives, but they're in equal or in the right ratio to cancel one another out. B, the point at which a molecule has no overall charge. That is the correct answer. C, the point at which the molecule is most soluble. That's the opposite. The pi is the point at which the molecule is least soluble. And D, the point at which a molecule can best bind salts. That's just kind of a curveball, tricky question or quick, tricky answer option. So yeah, no. The amino acid alanine is capable of which of the following charges? Okay, we kind of have a little bit of a cheat code with that because what you can see is alanine has 2 pKa values. So it has 2 ionizable groups. And every single amino acid has 1 ionizable group that goes between a positive and nothing, and then another group that goes between a negative and nothing. So whenever alanine is fully protonated, the carboxylate ion is carboxylic acid, and the amine is positively charged. So it's going to have a +1 charge. When everything's deprotonated, the amine is going to have no charge, and the carboxylate is going to be negative. So +1, 0, or -1 is our charge. The predominant or most common form of the amino acid lysine will have a charge of -1. And lysine, with its pKa's of, lysine has 3 pKa's. So I'm going to write them down on a piece of paper so I can transfer them down a little bit. 2.18. 2.18, 8.95, 10.53. Okay. What's not displayed here, but is something that you do need to be familiar with and do need to know, is where those different pKa values are found. So the lowest pKa is going to be the C termini, the mid or the 8.95 is the N termini, and the R group has a pKa of 10.9 or 10.53. So when all of these groups are protonated, this molecule will have a charge of +2. It will then, when it's deprotonated at one group, have a charge of +1 at 0 and -1. Okay, so these pKa's are 2.18, 8.95, and 10.53. Okay, so this amino acid lysine will have a charge of -1 when it is in a solution. The key word in this sentence is predominant. So the most common form will have a charge of -1 when it is in a solution with a pH of greater than 10.53. Now this is a subtle difference, but if the pH is exactly 10.53, the predominant form, well, actually there's not one singular predominant form. There's a form that has a 0 charge and a form that has a -1 charge. So the correct answer for number 22 is D. Now, number 23, 100% of the tripeptide lysine, arginine, glycine will have a charge of +2 at what pH? Now, to solve this problem, what we need is we need our pKa values, and then we need to figure out which pKa values matter. So I'm going to write out, I've already got my pKa's for lysine. That is KRG. Those are actually my wife's initials. So KRG, I'm going to write this out like such, KRG. And I'm going to do that because that gives me a way to only write the pKa values that I care about. So I need to know the N-terminal pKa for lysine. I already used that in my previous problem. It's 8.95. The R group for lysine is 10.53. The R group for arginine, I'm going back to my cheat sheet here, arginine, the R group is 12.48. And then glycine, I only care about the 2.34. I only care about that because that's my pKa for my carboxylic acid. So now, despite the fact that lysine and arginine each had 3 pKa values, I didn't care about all of them because some of them were wrapped up in peptide bonds. So I've got, what was it, 2.34, right? Yeah, 2.34. Nope, that's for alanine. Glycine is, yep, 2.34 also. So 100% of the tripeptide lysine, arginine, glycine will have a charge of +2 at which pH? So what's kind of implied here is I've got a charge of +1, +1, +1, and neutral. So this molecule will have a charge of +3, +2, +1, and then to 0, and then to -1. Okay. What I care about though is this right here, pK or pH, charge of +2. What I'm going to do is I'm going to write my pKa values in increasing order: 2.34, 8.95, 10.53, 12.48. Okay. If I want to figure out what pH where 100% of my molecule has a charge of +2, what I'm going to do is I'm going to take the 2 pKa's that surround that value. 2.34 plus 8.95 divided by 2 gives me 5.65, which is answer option D. Okay, I'm going to go ahead and just wrap this up in this one video, or in this second video. The tripeptide described in question number 23 can, under the right circumstances, have a charge of -3, +4, -2, none of the above. Okay, now let's take a deeper look at this, a deeper dive. I've got a total of 4 ionizable groups. 3 of them, at the lowest possible pH, will have a charge of +1. Those are amines. They're going to go from +1 to 0. Then I've got my carboxylic acid. That will go from 0 to -1. So when everything is deprotonated, that means that this group is neutral. This group is neutral. This group is neutral. And this group is -1. So that means I can have an extreme charge of -1 or +3. Now let's go back to the answer options. -3, can't do that. +4, can't do that. -2, can't do that. D, none of the above is our correct answer for this question. Next up, that is number 24. Okay, we're good. What is the single letter code for the tripeptide shown below? Okay, well, we've got, oh man, a funky looking double ring structure. Well, that's a hallmark of a tryptophan. If we look at answer options B through E, we've got tryptophan in there. Next up is a CH2OH. There's 2 amino acids that are hydrocarbons with a little hydroxide group that's going to be either serine or threonine. There's also a hydroxide group on tyrosine, but that's got a ring structure to it. So we're left with serine or threonine. So that gives us B, D, or E. And that last amino acid is glycine, our most flexible and our only non-chiral amino acid. And so our answer option is B, WSG, which is also one of my kids' initials. Huh, it's a funny thing. I use my family's name. Okay, so that wraps up the first part of this. In the next video, I'm going to go into the next exam. All right, well, I hope this was helpful.